Section 3.7, Implicit Differentiation. Okay, if we go to our topic that's on the AP exam, enduring understanding, the learning objective will be calculate derivatives of implicitly defined functions. Now, what the heck does that mean? Well, I'm about to show you. What I'd like you to do is try this warm-up, okay? And you're going to have to hit pause really quickly here because I want to see this is something, believe it or not, that we should know, okay, class? This warm-up here. So go ahead and hit pause. Take a shot at it. Can you write the equation of a circle with radius 2, center 0, 0? Okay, boom, hit that pause. Here we go. Now, here's something you should remember from your pre-calc days. The equation of a circle would be x minus h squared plus y minus k squared equals the radius squared. So in this particular situation, hopefully you were able to do this on your own. It would be x squared plus y squared is equal to r squared, 2 squared, which would be 4. Right? That'd be the equation of our circle. Now, if you remember, whenever it says find the equation of a tangent line, right, class, that'd be y minus y1 is equal to m times the quantity x minus x1. And we do know x1 is 1.5. If we know x1, we could easily find y1. But the question is we need to find m, which would be the slope of the tangent line. And how the heck do I do that if I have an equation here of x squared plus y squared, which is equal to 4? And that's kind of what we're getting after here in this section when we introduce implicit differentiation. Okay, so here it goes. If we have an equation that involves both x and y, in which y has not been solved for x, and we say the equation defines y as an implicit function of x, we may be able to solve for y in terms of x to obtain an explicit function, but redefining an implicit function as an explicit function is not always possible or easy. And I think that's the important word here, easy, or maybe we should use the word okay. Sometimes if we do something explicitly when we have an option of doing it implicitly, implicit sometimes, actually a majority of the time, especially in AP Calc, is a lot easier. All right, we're going to find the derivative of some of these guys, okay? Let's go ahead and do this with the knowledge we've known. Hopefully these 4 problems are okay. But the derivative of x squared, right, that would be a power rule. It would be 2x, okay, to the first. And then if we kind of wanted, now this right here is all in terms of x. So at the end, we would take the derivative of x, which would be dx, which is 1, which obviously we don't do because that would just be silly to do every time. However, if I take the derivative of y to the third, oh my gosh, did you hear that? That was some crazy thunder. But d dx, and if we do it with respect to y, we would do the power rule. But then I would have to take the derivative of y. And I would have to take the derivative of y with respect to x. So that's what that would actually look like, okay, class? Let's look at C now, right? We have a little bit of a product there, x times y. That's implicitly done right there. So how would I take the derivative of that? Well, we're going to take the derivative, we're going to write down x, and we're going to take the derivative of y with respect to x. Then we're going to take the derivative of x with respect to x, which would be 1, and we're going to multiply it by y. So that's kind of what that bad boy would look like, okay? And this is, once again, this is the first time we're dealing with taking the derivative of things implicitly. Okay, now here we go. How do I do this bad boy? Well, the derivative of x cubed would be 3x squared times dx over dx, plus the derivative of y squared would be 2y, but then it's going to change, right, because we're taking the derivative with respect to x. That's the important thing there. So it's dy dx. And then we're going to minus, right? We're going to take the derivative. Now I'm going to write this one a little bit different. Okay, then I have to do that. Okay, now that would be a product rule, right, class? And then I also would have to kind of distribute that negative sign there. So if I were to do this guy, I would get 3x squared plus 2y dy dx minus, okay, I'm going to keep this as a quantity, and I'm going to take the derivative of 3xy. I could have treated that 3 as a constant, but I'll keep that 3 with that x together, okay? So it'd be 3x times the derivative of y, which would be dy dx, plus the derivative of 3x, which would be 3 times y. Okay, distribute that negative in there. Okay, and we could simplify that bad boy up a little bit, but hopefully it's making a little bit of sense right now, okay? Because now we're going to get into how we use this in AP Calc, right? In AP Calc, we do a lot of different shapes. The problem with the warm-up, correct, class, was the equation of a circle. And I have it drawn right here for us, okay, really quickly. And the question is we're going to go over what it means to have a function written implicitly versus explicitly. Okay, this would be implicitly. Okay, but let's say I wanted to write it explicitly. I would solve this. Y squared equals 4 minus x squared. Y equals, whenever I take a square root of both sides, it is plus or minus. Okay, so that's actually the graph of the circle, right? The positive case would be the above the y-axis. The negative case would be below, right? That would be two semicircles. This piece right here being the y equals the square root of 4 minus x squared. This piece right here being the y equals the negative of 4 minus x squared, right? Which two semicircles makes a circle, okay? What does the graph of each explicit function look like? Well, I just got done saying that. Sorry, got a little bit ahead of myself. And it says find dy dx for the circle by differentiating the explicit function of x found in part A. Okay, so now we're going to take the derivative, but we're going to use the explicit functions to do it. Okay, so what does that mean? Here is my first explicit function, and I'll rewrite it, just kind of saving ourselves a step. Dy dx, right? That's notationally how we do that. We have a power rule, and when we do the power rule, we have an inside and outside, which means chain rule. Right? 4 minus x squared. Don't you dare touch that inside. We subtract it, but then we'd have to take the derivative of 4 minus x squared, which would be negative 2x. Let's clean up that bad boy, and we get negative x over the square root of 4 minus x squared, where if we go to the original problem, this bad boy right here is y. So if I wanted to rewrite it, I could get that. Interesting. Okay, now let's use these cool colors I got. Let's use blue. And we have y equals, and I'm going to do this for the entire problem, which is it's kind of a lot of work, right? Okay, but let's use the bottom half of that semicircle right there and find out what our derivative would be. Okay, notationally, the derivative of y would be dy dx. Everything's in terms of x. That's a power rule with a chain rule. Don't you dare touch that inside. Booyah, derivative of 4 is 0. Boom. Let's rewrite that bad boy. Oh, two negatives make a positive. Does it? I feel like I did something wrong. Did I? No. We have x over the square root of 4 minus x squared. This in relationship to this would be x over negative y. That is the same as that. What? All the rules going on that we have already learned have allowed us to compute the derivative of dy dx when y is written explicitly in terms of x. For an equation which defines y as an implicit function of x, we can compute dy dx without solving for y in terms of x. And that actually ends up being really nice. It saves a lot of time. Okay? And so we do want to follow these guidelines, though. So let's go over them real quick. 1, check. Differentiate both sides of the equation with respect to x. Remember, y is a function of x. Use the chain rule. 2, collect all dy dx terms on the left side of the equation and move all of the other terms to the right side of the equation. 3, factor dy dx out of the left side of the equation. 4, solve for dy dx. It is okay to have both x's and y's in your answer. Don't freak out if that happens, right? Okay. To find dy dx at a given point, plug both x and y into your equation you obtained in step 4. All right, sorry. Okay, getting a little crazy here with the weather we got going on. All right, example 3. Now, a lot of people do a lot better than reading those little guidelines. Let's just get some practice in, right? Let's go back to that equation of that circle we had, but this time, let's not solve for y. Why do extra work? Let's just take the derivative, but let's take the derivative implicitly. And remember, we're going to take the derivative with respect to x. That's important. All right, so if I take the derivative with respect to x, the derivative of x squared is 2x. And that would be dx over dx, which is 1. So we don't write that in there. That'd be a little bit silly doing all that work for such a short problem. The derivative of y squared would be 2y, but then it kind of changed, right? We have to take the derivative of y, which would be dy dx. And then this is where a lot of you make a mistake. What's the derivative of pho? Right? It is 0. And then what did it say? Well, let's get all the dy dx's on one side, factor if we need to, and then solve for dy dx. Okay, and then here, it's really just solve for dy dx, right? If I solve for dy dx, I think if you're in AP Calc, you can handle subtracting that y over, boom, doing that bad boy, simplifying negative x over y. Oh, snap, that looks familiar. Didn't we get that when we did it explicitly? Look at your notes. We sure did, okay? All right, it says find the equation of the tangent line at x equals 5. Boom, I'm going to do a little. Go back here. I just want to see what was going on at 3 halves. Let's make it blue up here at 3 halves. That'd be about right there. And that's a tangent line right there. Oh, snap. That's a tangent line right there. I actually have 2 tangent lines at 1.5 or 3 halves, right? We love our fractions in calculus or in math. Let's use fractions, okay? But it's asking me to find the equation of the tangent line. The directions were really good. It should have that little apostrophe, right? S right, then apostrophe in parentheses, right? So there's actually a couple, and I want us to get used to whenever we see that, find the equation of a tangent line to write y minus y1 equals m times x minus x1, right? And if we're going to do this bad boy, well, I'm actually going to get 2 answers. Okay, so let's go ahead and transform that. I need to know what my y1 is. I need to know what my m is, and I already know what my x is, right, class? Well, how the heck do I find y1? You do it real quickly. Remember, we always plug that x value into the original. And what's my original? It is right up here, okay? Ooh, my pen, I think, may have ran out. Hold on a second, class. Sorry, class, got to go back to this bad boy, right? But we get our equations here, right? We're going to find the equations of the tangent line. So I need to know my x1. I need to know my y1. Let's go ahead and plug that 3 halves, right, class, into the original problem there, okay, and solve for y. I apologize for the handwriting. I'm going to skip some of this stuff so we're okay. But if I do all that, I get plus or minus the square root of 7/4. So there we go. We kind of get our 2 answers here. If it's going to be y minus the square root of 7/4 equals slope x minus 3 halves. And then my other one would be y plus the square root, whoops, and why is it a plus? Because we have the negative case equals x minus 3 halves. Sorry, it's getting messy. I'm just going to try to finish this page off, and then we'll go ahead and do this in 2 videos. Okay, class? And now I just need to know what the slope is. Well, how the heck do I find what the slope is? Let's go ahead and do this little dy dx guy. And we're going to put a little line bar there. But there's 2 things that are important here. We're going to have to find out what our value is at 3/2, comma. Let me try to use this side of the pen. Holy snap, this is getting cray-cray. And then we have these square. Oh, my goodness gracious. This thing is wigging out on me. Let's go ahead and do dy dx. And we're going to do this for 3 halves, comma, the square root of 7/4. And if we plug that, right, we're going to plug that into our derivative that we had written out a little bit earlier. And if we go ahead and do some math on that bad boy, I got a negative 1.13389. And I'm going to go ahead and put that bad boy into that guy. Once again, class, it's all over the place. So we're making 2 videos out of this bad boy. We're 1.5, comma, negative square root of 7/4. And if I put that into the derivative, right, and our derivative, right, class, is just negative x. So it'd be negative x over y, right? That was my derivative. And so if I plug those values in there, I get this time a 1.3389, ... And that guy goes into that one. I apologize for that. I'm going to cut this off. That's part 1. Make sure you watch part 2 next. See ya in a little bit.